in a plane is of areas of inner polygons and lower bound of the areas of all outer polygons is called the of R and is denoted by A upper bar. The least upper bound of all inner polygons is the inner area of R, denoted by A lower bar. The inner area is always less than or equal to the outer area. In case the inner and outer areas are equal, then we say that R has area and define the value of the area to be equal to the common value of the inner and outer areas. In the present film, we shall see how this approach to area leads to the important concept of the definite integral of a function. We begin with a function which is positive, so its graph lies above the x-axis, and consider the area problem for the set of points under the graph. The only additional condition imposed on F is boundedness, so that the set in question will be a bounded set. The problem of obtaining the value of the area of a given set may be thought of as the problem of approximating either the inner area or the outer area by areas of polygons. Since we always have this inequality, the problem is to obtain smaller and smaller outer polygons or larger and larger inner polygons. Therefore, it is sufficient to consider only polygons of this kind, which are simply sets of points under a broken line graph. We may specialize even further to polygons made up of rectangles in this way. Consider the difference between the areas of the rectangular outer polygon and the given outer polygon. The difference is less than the area of a rectangle with base b minus a and height epsilon, and therefore may be made arbitrarily small by taking epsilon small. Similarly, we may approximate the inner polygon by rectangular inner polygons. Thus, for the set of points under the graph, only rectangular inner and outer polygons are needed in obtaining the inner and outer area. Our next step is to develop convenient notations and formulas for working with such polygons. Notice that a rectangular polygon may be constructed by first specifying the base intervals and then the heights of the individual rectangles. The endpoints of the base intervals form a partition of the interval AB. If there are n base intervals, the partition will involve n plus 1 points of division, starting with A and ending with B. Partitions will be noted by a small sigma. The kth subinterval I sub k, counting from the left, will have endpoints x sub k minus 1 and x sub k. Denote its length by delta x sub k. In order to obtain an outer rectangular region, the kth rectangle must have a height which is an upper bound for all of the values of f on I sub k. Hence, the smallest outer polygon associated with sigma, and therefore the best for approximating the outer area, is obtained by taking the height of the kth rectangle equal to the least upper bound of all the values of f on I sub k. The area of the kth rectangle is then equal to this product. The area of the smallest outer rectangular polygon, based on the partition sigma, is the sum of the areas of these rectangles, as k ranges from 1 to n. In the summation notation, it is equal to this. The numbers so obtained is called an upper sum for f, and for convenience is denoted by S sub f, upper bar of sigma. it follows that the outer area is equal to the greatest lower bound of all upper sums. Similarly, the largest and therefore best inner polygon associated with sigma is obtained by taking the height of the kth rectangle equal to the greatest lower bound of all values of f on I sub k. The area of the rectangle is then equal to this, and the area of the corresponding rectangular polygon is called a lower sum for f. It will be denoted by S sub f, lower bar of sigma. As before, these polygons are sufficient for obtaining the inner area. Hence, the inner area is equal to the least upper bound of all lower sums. Although we were motivated by the area problem to introduce upper and lower sums, the existence of least upper and greatest lower bounds depends only on boundedness of the function, and not that the graph lie above the x-axis. When the function has negative values, the definitions of the upper and lower sums still apply, though some of the terms involved may be negative. So we are no longer talking about areas of polygons, but only about numbers obtained in a special way from the function. It's important, nevertheless, to be able to deal with this wider class of functions. On the other hand, every bounded function is associated in a natural way with a non-negative function. Since f is bounded, there exists a non-negative constant c, such that f of x is always greater than or equal to minus c. Hence, if we add the constant c to f, the result is a new function, g, whose graph is obtained simply by sliding the graph of f upwards a distance equal to c. Now, return to the graph of f and consider any subinterval I of AB. Let m upper bar be the least upper bound of values of f on I. In the case of g, the least upper bound of its values on I is equal to m upper bar plus c. We are now able to relate the upper and lower sums for these functions. Let sigma be an arbitrary partition of AB and form the upper sum for f based on sigma. Recall that m sub k upper bar in this formula denotes the least upper bound of the values of f on the kth subinterval. We have just seen that the least upper bound of g on the kth subinterval will accordingly be equal to m sub k, upper bar, plus the constant c. So this is the upper sum for g. Next, we use properties of the sigma notation. Substituting, we obtain this. The sum of the lengths of the subintervals is simply the length b minus a of the full interval. We therefore arrive at this relation between the upper sums for f and g. Note that the quantity c times b minus a does not depend on the partition sigma. For convenience of writing, we shall denote this constant by r. Since the graph of g lies above the x-axis, the greatest lower bound of its upper sums is equal to the outer area A, upper bar, of the set of points under the graph. Therefore, we obtain this result. The greatest lower bound of all upper sums for f is defined to be the upper integral of f on AB. It is a number and is denoted by this special symbol. By a derivation paralleling that used to obtain the relation between upper sums for f and g, we may obtain exactly the same relation between lower sums. Since the least upper bound of the lower sums for g is equal to the inner area of the set of points under the graph of g, we obtain this result. The least upper bound of all lower sums for f is defined to be the lower integral of f on AB and is denoted by this symbol. From these relations, along with the definitions of upper and lower integrals, we obtain these equations, which may be written in this form. Since the inner area is always less than or equal to the outer area, the quantity A, lower bar minus r, is less than or equal to A, upper bar minus r. Therefore, it follows that the lower integral is always less than or equal to the upper integral. If the upper and lower integrals are equal, then we say that the function f is integrable on AB. In this case, the common value of the upper and lower integrals is denoted by this symbol and is called the definite integral of f from A to B. Not all bounded functions are integrable. However, the integral does exist for most of the functions which we have the occasion to consider. In fact, from the relationship between an arbitrary bounded function f and its associated non-negative function g, we see that the upper and lower integrals will be equal and f will be integrable if and only if the set under the graph of g has an area. It follows from this that any function which is monotonic or continuous on a closed interval is integrable on that interval. If f happens to be non-negative, then the upper integral is equal to the outer area, and the lower integral is equal to the inner area of the set under the graph. Thus, if the integral exists, it may be regarded as a formula for the area. It turns out that in many important cases, the definite integral may be evaluated in a very simple and direct way without the necessity of calculating upper and lower sums. This remarkable fact is based on the fundamental theorem of the calculus. When f is continuous, the problem of evaluating the definite integral reduces to that of obtaining a known function whose derivative is equal to f.